Good day and welcome to theme 3.7 where we will be discussing surface and flux integrals. So first we will be discussing surface integrals. Now in theme 3.6 we discussed how to get the surface area of a specific surface. So what we did is we parameterized the surface and then we used the cross product of the partial derivatives of the parameterization, and we got the magnitude of that and we used it to get our surface area, which gave us area. For surface integrals, we want to get the mass of a certain surface. Let's think about, perhaps you want to get the mass of your umbrella. So then first what you do is you parameterize the umbrella and you get the partial derivatives of the parameterization, you get the cross product and the magnitude, and then you use the density function of the umbrella to give you the surface integral. So this is a density function. This is not a vector, it's just a normal function. So this is just the basics of what the surface integral looks like. It works almost exactly as you would have worked with the surface area, except now we have the density function. And remember, if your density function is written in x and y, and perhaps you had spherical parameterization, then you have to turn the x and y into spherical coordinate types. So, an example. So determine the surface integral of the surface x squared plus y squared is equal to 4 with the density at any point of S equal to the distance from the point to the xy plane. So let's just analyze the question. So our surface is x squared plus y squared is equal to 4. So that's just our circle. And then the point of S equal to the distance from the point to the xy plane. So the distance from the point to the xy plane means that the distance is z, because any point to the xy plane would be z. So, and also what we've been given is that z is between 0 and 6. So this turns into a cylinder that goes from 0 to 6. So let's just first draw this surface that we have. So this is our surface we have here, and we can choose what we want to parameterize our surface as. Since we have a cylinder, we can use cylindrical coordinates. So our r would be equal to 2. So then x is equal to 2 cos theta, y is equal to 2 sine theta, and z is equal to w. So w just means z can have any value in between 0 and 6. So it's not a specific value. So it's not limited and it can take on any value between 0 and 6. Just remember it has boundaries. So then our parameterization would look as follows. We have x is equal to 2 cos theta, and we have our y, and we have our z. So our theta boundaries is between 0 and 2 pi, and this w is between 0 and 6, since z is between 0 and 6. So our density function, as I've previously mentioned, is equal to z, because that would be the distance to the xy plane. And now what we do, after we've parameterized, we get our partial derivatives of our parameterization towards theta and w, and then we cross product them and we get the magnitude. So we get the magnitude since it is a surface integral. We will go on about the difference later. And then what you do is you turn this density function, you change the z to w and get your surface integral. So here I've already changed it in terms of the parameterization to w. So our partial derivative towards theta is the following, and towards w it is this. And now we do our cross product, which would look like the following. So then to get your I cap, you just say 2 cos theta times 1 minus 0, which would just give you 2 cos theta. For our j cap, we say minus 2 sine theta times 1 minus 0 times negative 1. And that would give us 2 sine theta. And to get our k cap, we just say negative 2 sine theta times 0 minus 0 times 2 cos theta, which would just give us 0. Then to get the magnitude, we take the squares under a square root, which is the following, and we know that cos squared theta plus sine squared theta is equal to 1. So you will be left with square root 4, which would just give you 2. So now we have our magnitude of the cross product, and we've already changed our density function according to the parameterization that we've had. And now we have our surface integral. So here is the density function, and here is the magnitude of the cross product that you put. And our boundaries is 0 to 6 for w, and for theta it's 0 to 2 pi. And then you can just integrate it, since it tells you to evaluate towards w and then towards theta, and you should end up with an answer of 36 pi. Remember that at any time in this video you can pause it and try these questions on your own without my help, and then come back to see what was done. So for flux integrals, we will go into a bit more detail on the surfaces themselves. So the surfaces have to have direction, because flux integral works with vectors. So every surface has its own normal vector. So there are different types of normal vectors. We have downward normal vectors, which look like this. So you would have negative z values. And then we have upward, which would look like the following, which would have positive z values since they're upward. And then for closed surfaces, you get outward and inward normal vectors. So an outward normal vector would look like the following if you have a closed surface. And we take it as a positive direction for closed surfaces. So I will explain this later, but your z value in your parameterization needs to be a positive 1. And then for inward, we see it as a negative direction for closed surfaces, so your z value in your parameterization will have to be negative 1. Okay, so now that we've gone over the directions of the normal vectors, we will go on with an example. So in this example, they're asking us to find an upward normal vector on a certain surface of z is equal to x squared over 8 plus y squared. So first what we do is we rewrite this question. So it's not the normal way that we would find the vectors previous, like for surface integrals. So we rewrite it to get a function of x, y, and z. Since we want z to have either a negative 1 or a 1 value, we just rewrite it as follows. And then we get the gradient vector of our fxyz function. So you get the partial derivative towards x, the partial derivative towards y, and the partial derivative towards z. And just note that the partial derivative towards z will always be either plus or minus 1. So you have to manipulate this equation to have either a plus or a negative 1 depending on the direction of your normal vector. So this depends on the orientation of your surface. So in this case, for this specific surface, you can go draw it, but you will see that it will have, and it's supposed to have a positive 1. But as we've written it here, the partial derivative towards z will be negative 1. So if we want to have it as positive 1, we just multiply this by negative 1. and then this will be our result. So you just multiply it by -1 to suit the orientation that you have. And then we are going to discuss unit normal vectors. So we know what a normal vector looks like, but what does a unit normal vector look like? So to get a unit normal vector, we take the gradient vector that we've just found with the specific orientation that we want, and we divide it by its magnitude. So to get the magnitude of a vector, we just say square root over the square of your partial derivative towards x plus the square of your partial derivative towards y plus your partial derivative towards z squared. So that's just how you would find your normal vector. If you have the following parameterization, then this is what your normal vector would look like. To get your normal vector, you would just say the partial derivative of u cross-producted with the partial derivative towards v over the magnitude of the cross product. So that is what we normally would have done, but since we are now rewriting the surface so that we have an f of x, y, and z function, this is how we do it for flux integrals. Note that for surface integrals, we do not use normal vectors. So now we can talk about the actual flux integral equation and what it looks like. So for the flux integral, we have our flux function. So this function would have the following units. So it'll be the density times by the velocity vector. So density is kilograms in SI units, density is kilograms per cubic meters, and velocity is meters squared. So you will have kilograms per meters squared seconds, because velocity is meter per second. So that will be the units for our flux. So that just says how much of something goes through a surface. It's basically telling you how much fluid goes through a surface. That is what your flux integral will tell you. So our ds would then be, usually for surface integrals, it'll be the magnitude of the cross product dA. But for flux integrals, we use the cross product. And n is the cross product divided by the magnitude of the cross product. But since we have ds is equal to the following, this and this would cancel out and you will be left only with the cross product. So this is your final flux integral. It's the flux dot producted with the cross product of your partial derivatives. And remember that when you've parameterized your surface, you have to make sure that your flux integral is also in terms of those parameterized coordinates. So as I've said before, flux is the amount of mass passing through a surface per unit of time, and this is the unit that you would have for your flux.